Okay, let's start. Okay, chapter 8 will be related to your experiment report. Today we look at ductile and brittle fracture. So one of the accident or incident that we're familiar is the Titanic, right? Maybe not your time lah. There's a famous movie on the Titanic, a very old movie. So how this Titanic sink is because of the material brittle properties, right? So because during that time, the engineer do not when they fabricate this one, the material they use, they do not consider a very cold weather. So the material become brittle when it's go into those cold water. And another accident is Boeing 737-200. This one happened in 1988. As you can see, the small picture here, the whole fuselage, the section here blow off. So it's also because of the fracture failure, right? So let's watch this video. Okay, so this one you go home and watch it. Okay, so this one basically talk about this aircraft, how this body damage is because pressurization. So when you go up aircraft, the captain will turn on the pressure, internal pressure, so you will pump in air to equalize the pressure from outside and inside. So as you know that you climb higher, pressure outside is very low. But we are not designed to live in a very high place. So it means we're not used to low pressure. So to make you feel normal, the pressure inside the cabin was maintained at ground level pressure, right? So inside, as the aircraft climb higher and higher, the pressure outside is low, inside was high. So there's an expansion of your aircraft body. So then, material also, the material properties when you expand and then string again, expand, spring again, it fall under one category of failure called fracture, right? Brittle fracture. Okay. Okay, so failure, a loss of definition. Failure, it means a fracture of metals, especially failure. It means the inability of the material or component to meet these three items. Means that if the material unable to perform its original function, means it's also fall under failure definition, or it meet the performance criteria, although it may still be operable. So so it means inability component to meet performance criteria. So for example, in a previous chapter we learned about the tensile strength and the plastic behavior. So when the material already in the plastic region already, it can still use, but it cannot handle the pressure, the loading. So normal tensile graph, you have this one. So let's say we have this point, which is below the tensile or elastic region. So after elastic region, this is stress versus strain. So at this region, we call it plastic region. So when you conduct the experiment, the machine that you pull, right? So this is the force, kilonewton, and then when you turn, let's say you are pulling the aluminium sample here. You turn this one, then this one will pull, right? So at some point you reach a maximum. In the experiment, you see the red arrow and the black arrow. So after a certain time, you see the black arrow will come back to a lower value. That is when it reach a plastic region, and you see there's a necking, a coning. The necking start happening where the middle section become thinner and thinner, and it break. And it break. So today we'll look at how metal breaks after the plastic region. Okay. Okay, the rest you read. Okay. So we as an engineer, we should be familiar with the concept of fracture, because we want to make sure the equipment or devices we design is able to last long or meet the function that of that machine. And nowadays, our consumer products, actually the engineer was purposely designed for shorter life cycle. Now, what does it mean? It means product nowadays were designed to break at the faster rate so that you can buy the product again, right? So they just calculated up to a certain cycle. Let's say that, for example, the watch, your watch, the rubber, this one that you use, it was purposely designed to can last up to a certain years. Then it will become harder, and then it will broken, right? Okay. Now this is what you've seen in your experiment, right? Especially aluminium, the aluminium sample. You pull until then break pop. Then you will see this cup and cone phenomena. So fracture, what is fracture? Fracture is a process where new surfaces were seen, eventually lead to separation of component under stress into two or more parts. So fracture is you're creating a new surface. What I mean by new surface here is the area of that component, right? So when you break into, let's say this is a complete cylinder. This is the original surfaces, right? So how do you calculate the total surface of this component? Let's say you have this diameter D1 and the length of L. So the total area of this cylinder is the body times the two top and bottom area. How you calculate body area? 2 pi r times the length. All right, because the body is 2 pi r, the circle circumference plus 2 times pi r square. Okay, let's say you get a value of a total area. Let's say you get a total area 1. So by the definition of fracture means creation of new surfaces When the object break into two pieces, for example, you have two more area created in the body of the body. So let's say I draw something on the whiteboard here. You're creating these two more, means your equation, you have to plus two more area here. Right? So of course this area is small because it's when the metal you pull, it becomes smaller and smaller. Right? So this is the meaning of fracture. The keyword is the one I highlight on the screen here. If the question asks you to define fracture, asks you based on understanding, explain fracture. You write what we've seen is the creation of new surfaces or that leads to separation of component under stress. Right. So what we are looking at is a new surfaces and separation of component under what? Under load or under stress also can. Then we have two type of fracture, right? The two type of fracture. So on the screen here, you see ductile fracture and brittle fracture. By observation, you know which one is brittle, which one is fracture. If the diagram on the bottom, you see when they fracture, you see a flat surface. Flat surface means that it is a brittle fracture. If you see the fracture area is like a cup and cone, right? So this is a negative, this is positive lah. So it's like cup and cone, you can match together. So if you see this one means the material is ductile. So this one normally you will see in the forensic case study, right? Especially structure failure lead to the accident. They will look at the fracture surface, whether the object fell under which kind of fracture. Right? Keyword for ductile is slow crack propagation. The crack happening on the object is very slow. That's why there's a time to form the cup and cone shape. But the brittle, they happen very fast. You can only result a very flat surface. Let's look at ductile fracture. Ductile fracture, where does it happen? When it experience extensive plastic deformation. So on the tensile graph, stress versus strain graph, this is the region where ductile fracture happen. Sorry. Okay, this area, it happened, ductile surface. So on the diagram here, you see there's the type of material. So if you see a very sharp, then this one is very ductile or highly ductile. And this one, you see, still there's a necking here, means that there's a reduction of area. Then this one also under ductile, but not very high, just moderate. And then you see a very straight cutting one is called brittle fracture. So in assessment, this one normally appeared in section A, asks you to explain things that you can draw, things that you can draw and then explain. Normally it will be in section A. In section A, that you can draw and then explain. When you being asked to explain fracture or type of fracture, don't miss out the red arrow in your diagram. This red arrow is the loading or force that is pulling the parts. Okay. So your diagram, don't miss out the loading. Okay. So again, what is fracture? Fracture is a new creation, creation of new surfaces. Then it breaks separate into two or more pieces under loading. That is fracture definition. Okay. Now on sketch, on sketch. I'll give you. Now, how does the ductile fracture start? Huh? So as you can see on the screen here, when you have an object under plastic deformation, so under tensile loading, so there is a force acting in 3 axes. You know that deformation, strain definition, you have 2, right? Poisson ratio equal to laterate divided by longitudinal deformation or strain. Again, what is strain? Change of length and strain original or diameter. Change of diameter with original diameter. Okay, so this one, right, is molten. So this one is in 3 area, then some hole is forming, new surfaces inside there, right? So new surfaces is in a bubble form. Right, bubble is in sphere. So sphere equation 4/3 pi r cube, right? Okay, so 3 stages. First one, spaceman form neck cavities. Cavities is a hole. This is called cavity within the neck region. And then cavity, they join together. All these bubble, they join together. They become a bigger hole, or they call it crack. And the crack direction is perpendicular. The crack direction is in the lateral direction. So the direction is perpendicular to the force direction. The direction is perpendicular to the applied stress or applied forces, also correct. Why? Because what is definition of stress? Stress equal to force divided by area. So stress and force, they are linear relationship. So you can use either stress word or force. Then the third one, when it forms cavity becomes crack. Then crack will the third one will become cup and cone fracture that you see in the aluminum sample. So you can see here the crack, you start to have a crack. Then crack will find ways, weak point to destroy. So here you see the crack is a 45 degree and cup cone fracture is happening. So what is cup and cone? This is cup, right? Cup got something you can fill in, cup. Cone is like that. Is cone. So cup and cone. Okay. So if you see under microscope, you'll see like a bubble gum. It's like a bubble gum. You try to pull bubble gum. After the bubble gum break, you see you will like this one. Okay. So you want to see some this microstructure, you go and buy bubble gum, then you put into a fridge, then you try to peel it off, break off, you see this kind of microstructure, right? I'll show you, this is the video that's showing how ductile fracture happen on the sample, right? This one is on the aluminum sheet. Yeah. So you can see this one is in a slow motion. See this crack, we start to do this way, yeah. And by observing the crack direction, you know how the sample being pulled. Okay, the crack was moving from here to here. So the force is perpendicular to the direction of the crack. Okay. This is what you did in experiment, but this is on shaft. It's on shaft. So when you overloading your shaft, then the object will fail. The object will fail. So ductile, here ductile is very rare happen. Ductile very rare happen. Normally ductile, sorry, not ductile, brittle. This one is more on the shaft component. As you can see, this one already twisted. You see the line of twist. Then once I think 2 or 3 more rounds, then this one will break into 2 pieces. Okay, so all the power transmission component will face this kind of problems on the ductile fracture. Right, this plastic twisting and so on. So be careful if you use those non-certified material for your machine, right? So especially those vendors sell you in a very cheap prices. You need to be careful. Okay. Now brittle, you see the picture different from the previous one. Previous ductile is cup and cone. The significant features is cup and cone. The brittle is almost flat. Although you see some chip, some sharp corners here, but in general, it's just a flat line. Okay. So just now the brittle one, you see a lot of spike. But for the brittle one, you see got a very flat microstructure surface. Okay, the rest you read. So you learn about crystal structure HPC. HPC, they show brittle fracture. VCC, ion, and so on, also same. But VCC, they are brittle only at low temperature. Low temperature and high strain rate. What I mean by high strain rate? You do it very fast. Strain means the change of elongation. You do it very fast. You pull it very fast, right? Then you will see that it's brittle. It behave a brittle. But same metal, but you pull very slow, you will see cup and cone. It depends on how fast you pull it, and also temperature also. Okay, so high temperature, you will see ductile behavior. Low temperature, you will see it's as hard as a diamond or glass. Then you will see brittle fracture. So two factor lah. One is temperature, one is the speed of pulling. Okay. Now chapter 8, what kind of question will come out in your test 2 or final exam? To ask you to show some like way to prevent brittle or ductile fracture. So the main keyword is we are looking at whether you know how to elaborate temperature and your rate of pulling. Right? So you elaborate on these 2. Okay, so this is all the observation for the brittle. So if you zoom in, you'll see like a V-shaped chevron marking near the center of the fracture. So you see this one, also. See there's like an arrow here. Okay, so. And how you know that the direction or origin of the brittle or fracture? You see the lines, wrinkles, or especially this diagram. You see there's a line of ray here. They must be start from somewhere. So if you see this diagram, it will be in this section. We don't know the exact place, but it's from this direction, and then it start to back down. Okay. Okay, so this is how you explain the crack propagation. So you see this is the orange line here is the grain boundaries. Grain boundaries, and when you pull the object in tensile loading, pull at both ends, so the crack will be in the perpendicular direction. So the path of the crack will be in the red line here. And on the material science, this behavior, see this behavior, this process is called cleavage. Called cleavage. This one also you read lah. Okay. Okay. Brittle fracture also have 3 stages. Just now you see ductile, right? Ductile is start with a small cavity. Don't use the word bubble. Use cavity. Cavity turn into crack. Crack turn into cup and cone. That one for ductile. So there are few keyword there. So cavity. Let me show you the slides. For ductile, this diagram important. This diagram important. It start from stress. Then before it start to crack, you see necking. You see there's a change of neck. There's a change of neck. You form a neck. Once form a neck, then you form cavity. You draw small bubble here. Then after cavity, turn into crack, but still got a few cavity or small bubble here. But again, don't use the word bubble. Use cavity. Then the crack will form into cup and cone. This is cup. This is cup. This is cone. That one is a ductile. Brittle also have stages. Brittle is focused on slip plane. Also plastic deformation, but the dislocation happen along slip plane, and the shear stress will go and build up in the place where the defect happen, and micro crack is start to form. Okay, so brittle, important word is the slip plane. Slip plane, if I use the diagram on the whiteboard here. So let's say, crystal structures have their own orientation. So if the slip plane, they arrange like that, right? So brittle, if this one was this direction, then it will start from either one of the line here, and it will break into 2 pieces, something like that. Okay, so you start from plastic deformation, concentrate on defect. There's a defect on slip plane. So there's a defect inside here. Then it start to form into micro crack. Micro crack will turn into crack. This one is micro crack. Micro crack. This line is a slip plane. Okay, then this one is a crack. Or it become a 2 body already. Okay, so you see, just now the diagram for the ductile one is like almost like a straight line. But for the brittle, they follow the grain boundaries. You see the red color, right? They follow the grain boundaries. Just now, if you're comparing ductile straight line. Okay. Now we'll be more on calculation. So when it comes to formula, that is where we test your calculation. So how we derive the equation? We will give you the initiation of crack. On diagram on the left here, you have two initiation stage or two defect area. One is at the center, one at the side. So, but what is important is the A, is the length of the crack. This one is 2A. So this 2A will form a circle, or we call it cavity. All right, just now cavity very small, but you enlarge the cavity, you get like a bubble form. For bubble, we only look at half of the A, or half of the length. So this one is the cross section of X. And then you see this is the tensile loading, tensile test, pulling both ends up and down. So we are talking about fracture. Fracture, ductile material, you pull both ends, the propagation will be 90 degrees or perpendicular to the force, or perpendicular to the stress. Okay. Then you plot a graph. If you plot a graph, so x prime is the hole here, or cavity here. I'm not sure whether you heard about stress concentrator or stress concentration area. That is where failure start to happen. So you can see on the graph here is stress versus position. The higher stress will be at the opening of the defect. In this case, you see at the edge of the opening here, the stress is very high. And then at the perfect surface, the stress still there, but the stress is very low compared to the area of the defect. Okay. This is called stress profile for internal crack. Stress profile for internal crack. The rest I already explained. The area of high stress here, we call it, or this area, we call it stress eraser. The defect area, we call it stress eraser. They will raise the stress at that area. Okay, this also, the side, this one also raise stress eraser. The two, this one also can be stress eraser, this one also can be stress eraser. Okay, in engineering design, sometimes we need stress eraser. For example, if you want to tear the paper very easily, you make tiny hole to create stress eraser so that you're able to tear it very fast. And some of your phone protector, also it will create to propagate in the very fast direction. Okay. So maximum stress is at the tip. Is at the tip give you by one equation. This equation is important. Maximum stress or at the stress razor will be 2 stress at nominal stress times the A and rho T and square root. This is power half with a square root equation. Okay, so you have a nominal stress, maximum stress. You have the radius of curvature at the crack tip. This is the rho. This one, the curvature of your stress razor. A is the length of the surface crack, or half the length of the internal crack. When you do exercise or when you do question for your test or final exam, don't be confused by the question. You only use half of the length or half of the diameter of the crack. You only use the A. Okay, just take care of that. Don't confuse by the question. Okay, so if the question gives you diameter of the defect or hole, you divide by 2. Because this equation you use A. And remember to square root the answer. Okay, to square root the answer. Then there's a ratio called stress concentration factor. K is the ratio of maximum divided by nominal. So there's a constant value KT equal to stress maximum divided by stress nominal. So from these slides, you can actually predict how we ask question. We give you diagram, we give you parameter, then we will give you stress concentration factor. You find what is the maximum stress that able to handle by this object. Okay, either you find the nominal or maximum, or maybe you predict the A value. You predict the A value or predict the rho, the surface, the radius of curvature of the crack tip. So we have stress maximum, stress nominal, A, the length of surface crack, the rho is the radius of curvature, or the stress concentration factor. This is how we can test you. Okay. So if you move your equation, you move your nominal stress to the left, you'll get 2 and then square root of your A divided by rho. So by giving you stress concentration factor, you can find the A and rho. Or you can find the maximum and nominal. One of it will be missing. So you find the value. Okay. Okay. Now, just an observation. The value of K is high over here. Is high. Okay, let me draw. Okay, this one. If I draw a location, here, a small one, or here and no, here and the wall. Okay, so this is the tip. This is the tip. This is the wall. And then I give you 3 position, A, B, C. So if I give you the stress max stress nominal, you should able to predict, not predict lah, but you should able to like find, if you're given a graph, you should able to find the stress that appeared in that area. What do I mean? Huh? Okay, so this is a good graph that we can ask a lot of questions. For example, after we give you all information, I will just put a mark here, point B. We have given you a graph already. What is the stress at this area? Okay, what is the stress of this area? You just measure here to here. Then there's distance there. You just project up, project to the left. You get the stress. Okay. Then from the stress, you call back the previous chapter, the mechanical properties. So it asks you something about the force, or you refer back to the table of material. Then you extend to a lot of questions about material properties. Okay. Next equation for today, I think the second one for today, is a critical stress for crack propagation. This one for brittle material. This one for brittle material, it gives you by stress, critical stress equal to 2E epsilon, the modulus Young, and then the U divided by pi A. So the this one, this symbol is a specific surface energy. And again, the A here is half of the length here, right? You see on the diagram, huh? 1/2 the length of the internal crack. This equation is for brittle material, huh? Is for brittle material. The previous one is for the previous equation is for ductile material. Okay. So example one, example one. You read the question, see you're able to apply the equation, huh? So you are given a glass. You know glass is brittle, right? So subject to a tensile stress, if specific surface energy and modulus elasticity was given. So this one, energy was given. So you know you are actually using this equation. So you just substitute the value. Only need to be careful is the unit. This one is giga. Giga is 10 power 9. Determine the maximum length surface of floor that possible without fracture. It asks you without fracture. So you have this equation. You substitute the value. Before you substitute, you just rearrange this equation. The question asks you maximum length of surface floor, when it asks you about A. A is a crack. But again, what is A? A is only half of the length. So be careful on the A. It's quite tricky. So you rearrange, you'll get A equal to 2E, and then the specific surface energy divided by pi stress squared. This square here is critical stress. So here, the stress here, we use a tensile stress, 40, and then you substitute all the value. Stress calculator, you'll get 8 point something, 10 power negative 6 meter. Minus 6 is micron. Okay. So this is the maximum length of the surface floor possible without fracture. So this is A is 1/2 of the length of internal crack. It means if you use this equation, you are looking at 40 megapascal. This 40 megapascal, how it create the length of a crack, internal crack. Okay, the crack is 2A. A here. Okay. So this is how you use the equation. Okay, we have a short break. We continue 3 o'clock.